A few weeks ago, my phone rang. It was my nephew, who's diving headfirst into the world of building a CNC plasma table completely from scratch. But he hit a wall right out of the gate. He was stuck because the electronics wouldn't talk to his software. Nothing was moving, and he didn't know what to try next. Over the course of a week, he called me multiple times, completely baffled by the wiring. We spent hours going back and forth, tracing signals, and trying to figure out why this machine was refusing to come to life. It made me realize something important. I only had the answers to help him because a few years ago, I was the one staring at a pile of parts, completely lost, questioning every choice that led me there. This monster is my 100-watt CO2 laser cutter built totally from scratch. It wasn't because I couldn't buy one. I had very specific requirements that I wanted in my laser cutter. I wanted the CO2 laser to be in the 100-watt neighborhood, and I wanted a work area at least 24 by 36 inches. At the time, commercial machines with these specs would have set me back $10,000 to $15,000, which was just completely out of the cards. Building this machine myself offered a way to get the specs I wanted for a fraction of the cost. Part 1, the bucket list project. Before we dive into the guts of this thing, I want to be clear about the buy versus build decision. If you're looking to start a business and need a machine that works on day one to fulfill orders, do not do what I did. Go buy a turnkey machine. But if you're like me and you enjoy the process of building and learning as much as the process of making, then this is the ultimate project. My goal wasn't to have a perfect tool. It was to have a project that taught me more about lasers. And honestly, my laser isn't perfect, but I know the guy who built it, and if I want to improve something tomorrow, I know exactly where to find him. Now that I have everything wired up and I have a water pump pumping cold water to cool down the laser tube, it's now time to test fire this 100-watt CO2 laser tube. I'm really pretty nervous about test firing this because this is the first time I've test fired any CO2 laser tube, let alone this one in particular. 3, 2, 1. Holy crap, look at that. This thing is scary. It like burned a giant hole. This is 3/4 inch plywood. Can you imagine what it would do if I put the focusing lens on there? That thing would go right through this piece of wood. If I wasn't scared of it before, I sure as heck am now. Part 2, designing for progress. I started this build in Autodesk Fusion, but I made a conscious choice not to over-design. I've seen people spend years in CAD obsessing over every nut and bolt, and they never actually cut the first piece of aluminum extrusion. I didn't want perfection to get in the way of progress. I used a parametric design for the frame, which gave me a safety net. I knew the general dimensions I wanted, but I didn't solve every mounting bracket or sensor placement on day one. I chose aluminum extrusion because it's forgiving. It allowed me to treat the build like an evolving prototype. This is the CO2 laser tube that you saw in part 1 of the video series. It's just a giant glass tube, and so I need to figure out a way to mount this to my frame. So I need to design and 3D print a mounting bracket for the laser tube that allows me to screw it into the frame and give me a little bit of adjustment. So here's what I've come up with. I've got this little bracket that will actually slide into the aluminum extrusion just like this, and I can tighten those screws down and adjust the height here. The laser tube will kind of sit in this little slot, and I've actually designed in little holes for a zip tie to go around and kind of cinch down and tighten that tube to these mounts. This should provide a really great way to mount the CO2 laser tube and be able to adjust it up and down. This is a perfect place to demonstrate how to use these little internal brackets to mount this laser tube mount. So I'm going to slide 2 of them in like this into the T slot. And then I can slide this piece over top of those brackets and then tighten down the nuts, and that creates a really strong joint. Of course, I've printed a second one of these tube mounts, and that will go here. That will allow the laser to sit in these little mounting brackets along the back of the machine. So as you can see, if I would have used this triangular gusset style of bracket, it would have been in the way when I go to slide in the 1/4" acrylic to enclose the machine up. But by using this little internal 90-degree style, I only have to notch out just a little bit here, and I can slide a panel in here and it will make everything look really nice. Let me just quickly go over the construction of this frame. Like I said, I used aluminum extrusion. A lot of the bigger pieces are 20 by 40 millimeters, and then some of the smaller structural pieces are 20 by 20 millimeters. Because I was able to buy all of these aluminum extrusion pieces at the right length, the only waste I've had so far in this whole project is this little 1-inch piece right here. Speaking of length, let me tell you about the dimensions of this machine. The width of this machine is 1,500 millimeters wide, and it is 1,000 millimeters deep. It's about 250 millimeters tall, so this should allow me to fit pretty large pieces of material in here without worrying about size. Part 3, Future Zach and the Efficiency Myth. This build-as-you-go strategy meant I became very well acquainted with somebody I call Future Zach. Whenever I hit a problem that felt too complex for the current stage of the build, like how to route the air assist lines or where to tuck the motor drivers, I'd just say that's a problem for Future Zach. Now, was this the most efficient way to build a machine? Absolutely not. I had to take things apart more than once. I had to slide T-nuts into channels I'd already capped off. But trying to be perfectly efficient is an impossible expectation. In the previous video, I 3D printed some little plates that had wheels on them. The 3D printed parts would have worked just fine, but they were more of a proof of concept. Now that I know that's going to work, I've gone ahead and I've ordered some aluminum ones. These will be a lot stronger and more durable in the long run. The laser head mount is ready to go. It can slide on the y-axis here, like this. The problem here is that this aluminum piece is too long. I bought it at a length of 1 meter, but because of all the hardware that I have installed, it needs to be cut shorter. It's really critical that I get this measured correctly and I cut this to the right length. I only bought one of these and they're pretty expensive, so I don't want to mess this up. Okay, here's the moment of truth. Do you think I messed this up or do you have faith in me? Let's see if I got this dimension right. Oh my gosh, are you kidding me? That worked out perfectly. Now I can attach these plates onto the end of this y-axis here. And in order to do that, I'm gonna need to tap the holes that are at the end of this piece of aluminum. Luckily, the plate already has holes that are in the right spot, so I don't have to do any drilling there like I did on the previous one. But I do need to tap these holes in, and then I'll attach these plates to the end. This is the little plate that the aluminum extrusion needs to bolt into to slide along the x-axis. I'm having a little bit of interference between the aluminum extrusion and the head of the bolts, but I think I can use a little Dremel tool to shave down the aluminum extrusion so that it doesn't interfere with these bolt heads. If I had waited until I had every answer, I'd still be staring at a blank screen. Assigning those unknowns to Future Zach kept the momentum going. When Future Zach eventually inherited those problems, he didn't panic. I just hopped into DigiKey, ordered the exact right terminal blocks, connectors, or cable management clips, and I just kept moving forward. I didn't mind that the route wasn't a straight line. The detours were usually where the actual learning happened. I knew this was gonna happen. I forgot to put the laser head on before I screwed both of those plates on. Now I've got to take one of them off and slide that laser head on. The order of operations in this whole assembly has been like the biggest struggle. I have to get everything in the right order, otherwise I have to take things apart and do it again. So that's what I have to do. I've got to take off that last little plate and slide on the laser head. Part 4, prototyping in plastic. One of the best tools I had during the build was my 3D printer. Almost every major plate on this machine started out as a 3D print. It was a fast, cheap, and easy way to get the gantry moving and confirm my geometry. Once the design settled, meaning I'd used the machine and confirmed that the motor mounts weren't going to flex or fail, I had a choice. I could leave the plastic parts or I could replace them with metal. Eventually, I moved to fabricating metal parts for the high-stress areas using professional services or my own manual tools. But using 3D printing as a bridge allowed me to test the machine in the real world before committing to expensive materials. It's a great way to fail fast without breaking the budget. This linear rail material is super hard. A hacksaw with a normal metal cutting blade is not going to get through this material, so I'm going to have to use a cutoff disc in my Dremel. Oh my gosh, that just totally split that piece of aluminum. Part 5, when things go wrong. You have to expect things to go wrong, and for some reason, they always happen late at night when you're inches away from a milestone. I remember finally getting the water cooling system plumbed and ready. I bought an expensive professional water chiller, assuming it would be the easy part of the build, but I couldn't get it to talk to my controller. This is the electrical connector that has the signals that tells the laser controller whether or not there's water flowing and if it's safe or not to turn on the laser. In the owner's manual over here, it says that pin number 2 here is connected to the normally closed terminal of the relay. But if you look at pin 2 on here, there's nothing connected to it. So there's no way for it to tell me that there's not water flowing. I ended up having to open up this $500 piece of equipment at midnight only to find out it was wired incorrectly from the factory. So that's really annoying because this thing was supposed to tell me whether or not there's water flowing, but it's not working properly, and of course I'm gonna have to troubleshoot it and figure out a way around it. But I think I got it. This is the relay that I need to figure out which of those is that normally closed terminal, and then just wire it to that pin 2 over there. So it's not terribly hard, but it's just really frustrating that an expensive and professional solution like this doesn't come wired like it's supposed to. The flow sensor relay was literally soldered to the wrong pins. If I had bought a turnkey laser, I would have been calling tech support and waiting weeks for a replacement. But because I was already in the project mindset, I just grabbed my soldering iron and I fixed it. That's the beauty of building it yourself. You aren't intimidated by the machine because you've already seen it in pieces and you know that any broken component is just a quick search and an overnight shipment away from being resolved. And that brings us right back to my nephew. When he called me up completely stuck on his plasma table, he was facing that exact same wall. He was ready to give up for the week, but because I had spent those late nights troubleshooting my own wiring disasters, I knew exactly what to look for. We hopped on the phone one last time, walked through the pinouts step by step, verified the signals and hit the switch, and guess what? It worked. That first stepper motor spun to life right on his bench. And I cannot tell you how incredibly rewarding it was to pass that knowledge down and hear the sheer excitement in his voice when it all finally clicked. But I only had those answers to give him because I had blundered my way through my own mistakes on this laser cutter. If you were to ask me what I learned from building a giant CO2 laser cutter, I could give you the technical lessons that I learned or the troubleshooting steps that I took, but ultimately, I think that the real takeaway is this. The frustration you go through on your own workbench eventually becomes the blueprint you use to help the next generation on theirs. One of the things that I need to do to take this project across the finish line is to put some panels in to enclose the machine. So I'm going to enclose it using some aluminum composite material. I originally got some cheap plywood to do this part of the project, but once I discovered this aluminum composite material, it was clear that this was a much better choice. The core of this material is made out of a high density plastic, and then the surface is covered in a thin layer of aluminum sheet on both sides. This material is just the right thickness to slide into the slots in the aluminum extrusions. I even added a little cutout so that my fasteners don't interfere with the panels. Part 6, a project, not just a tool. My laser cutter isn't the prettiest one out there. The wiring in the back is a little longer than it needs to be. There are a few extra holes in the extrusion from my early mistakes, but it works and it works well. I didn't build this just because I needed a laser. I built it because I wanted to learn how to build a laser. I wanted a machine that I could modify, break, and fix without fear. If you want a tool that earns you money on day one, go buy one. But if you want a project that teaches you about motion control, optics, electronics, and you don't mind a few late nights troubleshooting, then build it. I'm glad I didn't wait for perfection. I'm glad I left those problems for future Zach, because now the project is done, the tool is working, and I'm ready to tackle my next bucket list project. You may not be building a giant laser cutter big enough for you to fit in, but I'll bet you have a project that you've been working on for a long time or wanted to get started for a long time. I want to challenge you to stop waiting for the perfect time. Go get started on it today, even if that means just opening up a CAD file or going onto DigiKey to order the first couple of stepper motors and microcontrollers to prototype on your bench. You'll be surprised by the burst of motivation that follows as soon as that project moves out of your head and onto your workbench. I don't know what I'll be working on next, but I do know that I want you along for the ride.